Yeah, hello, welcome back. It's been a while around here. Had some issues with my recording software, and it was recording. It was basically making my screen half, and had some trouble setting it up properly. Even some of my other videos, you could see that after production, some part of my explanations were cut short, and that was not intended. So I was really trying hard to find a way to fix it, and I'm glad to say it's fixed now, so we can get on board with the serious stuff. So today we're going to be discussing EIGRP. We are going to be taking a look, a basic a deep a kind of deep level overview of the protocol. All these features here, I will explain them. All the features from top down. I'll explain what it does, how it works, and then subsequently I will upload short videos of each feature here, and do a little explanation. Then excuse me, then we'll hit the labs and configure all of this. So the idea is to make this video to not cram everything into one video and it gets boring. So if you are with me on this, let's go. Clear my screen here. Okay, so EIGRP. EIGRP actually stands for Enhanced Interior Gateway Protocol. That's the full meaning of EIGRP. It is regarded an advanced distance vector protocol Okay, why is it called an advanced distance vector protocol? First off, EIGRP is a largely Cisco proprietary protocol, although Cisco has released the code for EIGRP for other vendors to implement, but even up till now it is still considered Cisco proprietary by almost everyone. So there are two types of routing protocols for IGPs, that's interior gateway protocols. We have the distance vector protocols, and we have the link state protocols. Down here we have ISIS, we also have OSPF, and this is where we'll have RIP, and we'll have EIGRP here. I bet that EIGRP has an advanced in front. Okay, why EIGRP is called an advanced distance vector protocol is that it combines it gets a combination of some behavioral traits. You get behavioral traits of link state protocols into EIGRP. So for example, one is that EIGRP forms adjacencies. If I can spell adjacencies right. It forms neighbors. Let's use that word. It forms a neighborship. It forms neighbors with its directly connected links. So it will form a neighborship or adjacency. That is one. It will utilize keep alives or hello protocols to keep the neighbor alive, to say, hey neighbor, all the routes I have sent you, they are still valid. So I'll use this hello to say I'm up and all the links I've sent you, there has been no issues. Whereas in the other routing protocol, distance vector routing protocol named RIP, it doesn't form neighborship. It just sends its whole routing table, like I explained. For version 1, it will send it as broadcast, and then for version 2, it utilized multicast to send the whole of its routing table every 30 seconds. EIGRP is not like that. EIGRP behaves more like the link state protocols that will form neighborship, send keep alive to make sure that each neighbor is your neighbor is up, and then exchange keep alive to say that their links are fine, instead of sending the whole routing table at each interval. EIGRP also utilizes a metric. Let's talk about the algorithm. EIGRP utilizes the dual algorithm. This is the diffused update algorithm. That is what EIGRP uses for each route calculation and doing the metric calculations and picking the best routes and all, picking the successor route, choosing the feasible successor, convergence time and all. It uses this algorithm. That's the EIGRP. That's the algorithm that the EIG protocol makes use of. Okay, so let's continue. Like I said, it forms adjacent neighbor with its directly connected neighbor. So how does EIGRP form neighborship? I'll clear my screen here. Clear this screen. Okay, how does EIGRP form neighborship? So let's assume we have router 1 here directly connected to this router 2. To form a neighborship, once you have configured EIGRP, the command to configure EIGRP for Cisco is router EIGRP, then an AS number, an autonomous system number. An autonomous system is a group of devices, a group of networks under the same administrative domain. So a group of networks, let's say managed by Coca-Cola, that they will have their own AS. So Coca-Cola will have their own autonomous system that they use in their network to run in their IGP network. So a group of networks under the same administrative domain is called what? An AS. So that is an autonomous system. So once you have configured this on the router and you have indicated the interfaces that you want or the networks that you want to run EIGRP, then EIGRP will first start by sending a hello message, a hello packet to a multicast address 224.0.0.10. That's the multicast address for EIGRP. Once router 2 is configured, he will also send a hello. This is how EIGRP discovers neighbors. Sends a hello to the same multicast address. Once this neighbor is discovered, every other thing, neighbor discovery is via what? Multicast in EIGRP. So once the neighbor is discovered, they can now exchange routing and topology information via unicast. So for EIGRP neighbor formation, what are the key steps? 1, multicast is used for neighbor discovery, and 2, unicast is used for route exchange. So that is how EIGRP will form a neighbor. Okay, pick another pen here. Metric. Metric is what a routing protocol will use to decide which path is the best path. So for instance, let's say we had R1 here connected to R2, connected to R3, and R3 has a network here 3x, let me make it as 3x, and R1 is also connected to a router R4 that is connected to R3. So we are going to say, okay, that the cost for R1 to R2 is 4, and the cost for R2 to R3 is 4, and the cost for R3 to this directly connected network is 1. Don't mind, I'm using little numbers. For EIGRP, these metric values are actually very large. They are very large numbers because of how EIGRP compares its metric. So let's also say that this link is 2 and this is 1. So EIGRP, or let's actually make this link the worst link. So EIGRP will use metric to decide, because R2 will advertise to R1 the network 3x. R4 will also advertise the network 3x to R1. So for R1, he now knows about network on his table. He now knows about network 3x via R2, and also network 3x, this is in its EIGRP topology table, via R4, this is R1's table. So metric is what EIGRP will use to decide which route out of these two routes makes it to the routing table. So the metric for this route is a combination of all of these costs, what it costs each router to get there, and I will tell you how EIGRP does its calculation. So for R1 is saying to get to the link to the network 3 is going to cost him 4 plus the 4 it costs router 2 to get there, plus the 1 it costs router 3 to get there. So this link is costing a total of 9, and this link will cost a total of 20 plus 1 plus 1, which is a total of what? 22. So EIGRP will pick the lower cost route as the best route to the routing table. Remember, for RIP didn't mind the cost of the bandwidth of the interface. RIP just said how many hops away. So RIP utilized hop count for each metric, but EIGRP utilizes a composite metric. The screen is already filled here, so EIGRP utilizes a composite metric. This composite metric, I'll list them, is bandwidth, we have load, we have delay, we have reliability, and we have MTU for EIGRP. So EIGRP will check the bandwidth on the link. It will also take into calculation the load, take into calculation the delay, take into calculation the reliability of the link, and the overall maximum transmission unit of the link. But by default, these are K values: K1, K2, K3, K4, and what? K5. 5. So by default, EIGRP uses K1 and K3, that is bandwidth and delay for each metric calculation. It does not take into consideration all other K values because only K1 equals 1 and K3 will be equal to also 1 in the metric calculation. Every other K value is equal to 0, and EIGRP uses a very, very ambiguous formula that I wouldn't even want to bother my head to write it. So look it up and post it in the comments. Let's have fun. You don't want to do that with your head, but that's how EIGRP calculates metric. So the next one is key takeaway here is that metric is what a router uses to decide the best path for a particular route when it has multiple routes coming from different neighbors. Unequal cost load balancing. EIGRP actually is the only IGP that uses this unequal cost load balancing. Like I was saying, metric is what you use to decide which route is the best route, and the best route always make it to the routing table. Best route and goes into the routing table. Other routes that are not the best routes, second best route or second best for EIGRP, they go into the into the topology table. They don't go into the routing table. They go there and wait. When the best route goes down, then EIGRP will check its topology table to see if it has that route in the topology table. It will now inject it into the routing table, and forwarding continues immediately. But for EIGRP, unequal cost load balancing means that instead of having only the best route in the routing table, you can have best route and second best route, both of them into the routing table. So EIGRP will now, the router will now do a kind of load balance. Let's say we have this link and also this link to the same network 23. So R1 says, okay, via this link is actually a cost of 3, and via this link is actually a cost of 1. So R1 says, okay, actually this is my best route to this network 23, and by default we install this in the routing table and then put this into its topology table. But when you now configure a feature called variance, you can make EIGRP put both this part via R2 and the part via R1 into the routing table, and now you do what? An unequal cost load balancing, in the sense that the router can decide to say, okay, for every 3 flows that I send to this network 23 via this part, I am going to send 1 flow via this part. That is what unequal cost load balancing is, and that is what it does. Clear my screen also. EIGRP terminology. EIGRP actually has many terminologies that we need to know about. So you hear about advertised distance. This is simply my neighbor's metric. So R1 is connected to R2, R2 is connected to R3, and we have network 34 here, we have R4 here, This is network 34. So advertised distance for R1 from R2 will be R2's metric to the link. So if R2 is cost is 2 plus 1, his advertised distance to R1 is going to be what? 3. That is what advertised distance means. It is simply my neighbor's metric. That's the very simple way to look at it. Another one is the feasible distance. Feasible distance is my metric. So we are taking ourselves as the what? Router. So the feasible distance for R1 now, if this is a cost of 5, is going to be 5 plus 2 plus 1 is going to be equal to 8. That will be the feasible distance for R1. Okay? Talk about successor. A successor is simply the best route. It is the route that makes it to the routing table. That's the route that is always installed in the routing table. That is what a successor is. I have explained how a successor comes about. A feasible successor, get a black pen. Feasible successor for EIGRP, feasible successors work different way. For EIGRP, out of all the IGPs, EIGRP is the fastest when it comes to what? Convergence. So EIGRP actually converges very fast. For Cisco says is sub-second, that the time it takes for EIGRP to move from the successor route to a feasible successor is you can call it is negligible. You can't measure it. It's negligible. So for EIGRP to consider a route to become a feasible successor, that is a route that is candidate for being moved. That is a route that is candidate for being moved to go from to have that subsequent convergence where EIGRP was forwarding via the successor route, and so all of a sudden it loses the successor route and changes a split-second convergence to the feasible successor. Something, a clause has to be met, and that is what is called the EIGRP feasibility condition. So, not doing a lot of quotes here. I will not. Okay, maybe I'll write it down. So to be considered a feasible successor, the advertised distance, let's call it AD, the advertised distance of the route must be less than the feasible distance of less than the feasible distance of the successor. That is the route that is in the routing table. What this is actually saying is that for me to consider a route a feasible successor, that route metric, so let's say in this case we have 5, 2, 1 and 8. So the feasible distance for this route for router 1 is 8, and this link is a cost of 5, and for this guy this is a cost of 2. So the advertised distance for this route to R1 is going to be what? Is going to be what? 2. So when router 1 gets this advertised distance, he's going to look at it and say, okay, what is costing you is what? Is equal to what? 2. And my feasible distance for the route that I've actually chosen to become the best route is 8. For example, don't mind so much what the whether it's tallying, is 8. Then that route can be considered to become what? A feasible successor. That means EIGRP will install that route in the routing table, and if the best route goes down, in any scenario that it goes down, the feasible successor immediately is put into the routing table, and that link is utilized in forwarding. And that is the advantage that EIGRP has over almost all the IGPs, and that is why you have seen it. Most of the financial institutions deploy this routing protocol in their IGPs, at least down here in this part of the world where I am. So why they do that is that the advantage is that you can easily manipulate the metric of a route to the point that EIGRP considers that route to be a feasible successor. So in deployment, that is what the strive is to do. You do that, you manipulate the route. Once you have a second path, even though usually you will not leave it by default, you will manipulate that route so that it becomes a feasible successor. And once the successor route goes down, there is split second convergence. This is faster than any IGP, including OSPF, ISIS, or RIP. Any of these IGPs, EIGRP converges faster than any of them. Convergence means regaining state and forwarding and having a path to the default network that you are forwarding to. So that is that about some of these terminologies. Talking about tables, EIGRP keeps 3 tables. Number 1 is the routing table. The second one is the topology table. And the last one is the neighbor table. So these tables, what goes here? The successor route will go here. Successor routes end up here. Feasible successors or other routes end up here, and others. And then this is a table for all the neighbors that the router that is running EIGRP has. Filtering using ACLs. Here we'll look at filtering down with prefix list. We'll filter with prefix lists as well as ACLs, but this I think is better done than said. Moving on, we'll go to summarization. So if I had a network R1 and R1 is connected to network 1.1.0/24, 1.1.2.0/24, 1.1.3.0/24, and also 1.1.0.0/24. For instance, and R1 advertises this route to R2. For R2 is going to have a bunch of routes 1.1.0.0/24 via R1. The same thing 1.0/24 via R1, 2.0/24 via R1, and 3.0/24 via R1. And if R2 is advertising the same to its neighbor, it's going to advertise all of these routes once more. So you find out that the routing table gets bigger and bigger. So one of the things you can do is to summarize these routes into one advertisement, and EIGRP allows you to do that. So we can easily summarize this route to 1.1.0.0/22. So all these networks has been collapsed into one advertisement, whereby we can now advertise a single route to router 2, and router 2 will also do tours to router 3, and we thereby reduce the routing table, so the number of routes in the routing table. So instead of having all of these routes, we are going to have just one route that says 1.1.0.0/22 via R1. So that is what summarization does for you. It can also help you. You can also do a little bit of filtering with summarization. Okay, and we'll talk about EIGRP leak map feature. What is leak map? When you summarize some routes, let's say for instance we have summarized 1.0, we have summarized all of those networks into this, we can also use a leak map to say, even as I'm summarizing this route, I want to still leak the specific route 1.1.3.0/24 to my neighbor. So you still leak some specific routes to your neighbor. That is what the leak map feature does. You leak specific routes even after you have summarized to your neighbor. Remember the rule of routing specificity, that the longer march always wins. So if you need some specific routes on your neighbor so that matching is easy, you can always leak some specific routes to your neighbor. For authentication, EIGRP actually uses 3 types of authentication, one of which is clear text. EIGRP utilizes clear text. Number 2 is MD5 hash, and number 3 utilizes SHA, although this can only be utilized when you are running in named mode. For the normal EIGRP router EIGRP 10 or 100 or anything, you can only utilize these two. So what does authentication do? Authentication proves that router 1 is who he says he is. So you authenticate him before you can exchange routes with him, so that we can prevent a user X here that will configure his laptop and start pretending to be an EIGRP speaking device. Named mode is simply the same EIGRP, but now the named mode is much more, I would say it's much more modular in configuration, and instead of having a scattered configuration, in named mode everything is modular. you have address families there, you have the autonomous system, even the configuration that you are going to do on the interfaces. You do it inside the EIGRP global protocol, the global command, instead of having a scattered configuration. Name mode brings together all of the configuration into one place. It's more like how the iOS XR does configuration for some of these things. So EIGRP name mode is still the same EIGRP, but much more modular than the normal one that you may be used to. And then we'll also look at how EIGRP works over DMVPN. We'll still look at DMVPN in detail, but we'll look at how EIGRP works when you use it as the IGP, both for phase 1 and phase 2. For the IGP, this is your internet. So we'll look at how EIGRP works when you are doing DMVP and dynamic multi-point VPN. And then EIGRP stub routing deals with, okay, I have to calm down to explain this. So if router 1 is connected to this network and router 2 is just connected to this branch office, let's say it's router 10, that only services the branch office routers, and its only exit to the core is via router 2. So, and router 2 now loses, let's call it a network down here. Let's say is the network 100.x.x.x/24. Router 2 is going to send a query to all of its neighbors, asking if anybody has a route to this link that it just lost. So it will send a query to router 3, send a query to router 4, send a query to router 1, and also send a query to router 10. And it starts to wait. It must wait till it gets the query replies from every router. But the funny thing is that router 10 here is not involved in the core routing. It only uses router 2 to exit. So to reduce the scope of query propagation, you can configure this router 10 to become a stub router. And when it becomes an EIGRP stub router and router 2 loses a network, it is not going to send this query down. This query will not be sent to router 10 because router 2 knows well that this is just a dead end. So stub routing is used to mitigate or reduce, the right word is reduce the scope of query propagation. So by default, queries are propagated to all neighbors. But if you have a dead end that will not have a reply to your query no matter what, that does not have a backup route that is taking it to the other core devices, there's no point asking it for if it has any of these missing networks. And also in query propagation, that's where you have what we call the EIGRP stock inactive. Stock inactive, when this happens, EIGRP will send queries to each neighbor, and if this neighbor had other neighbors, let's say R7 and R8, R3 will also send this query to its neighbors and start to wait for replies from all of these neighbors. If no reply, if he doesn't get all the reply from all of his neighbors, and these guys will also continue to send queries to their directly connected neighbors. So it's an endless querying for a single route that was lost. So if router 3 is not able to reply router 2 after a given time, router 2 by default will consider that neighbor to be down just because it has not replied its query. So Cisco came up with a solution for that. so that when router 3 has not replied a query, instead of router 2 bringing down the neighborship, it will send it a message to say, are you in stock in active? That means you have not gotten back your queries from all your neighbors, and router 3 will respond to say yes. So router 2 will keep the neighborship up, knowing that router 3 is still up, just that it is what stock in active. So down the line, we are going to take a look at all of this and configure all of these features together. So I hope you are here with me for the long run. Thank you for viewing. I hope this has been informative for you.